agency, and his research deals with many different topics in numerical prediction, ranging on several scales. I'd say from the sub-seasonal to the interdecadal scales, and several topics on predictability. Today, Yuhei, I think you will follow what you showed us on the first seminar. That is, you show us a novel technique based on the information theory, and you and your colleagues applied this technique to address some causal relationships on between one of the most interesting sources of predictability on the subseasonal scale, that is the snow cover over the northern hemisphere, and the predictability of surface air temperature. Yuhei, we are ready to listen to you. Please.
Thank you for the kind introduction. So, yeah, today I'm going to introduce some works we did recently. And yes, I'm a researcher of Meteorological Research Institute. I'm mainly working on the seasonal prediction. And my research interests are on climate dynamics, monsoons, tropical cyclones, and atmospheric ocean land interaction. In this seminar, in particular, we will focus on the land atmosphere interaction. I'm a member of the WMO working group on member of the standing committee on the WIPS, SC WIPS, and member of working group on subseasonal to interdecadal prediction in WCRP. And also, I'm involved in the WWRP S2S application for agriculture and environment project, which has been recently launched. Okay, the introduction. So we all know that the land is an important component for the S2S predictions. So this figure is a very popular figure showing that the sources of predictability in S2S timescale. So in very short range, the initial conditions, the information basically came from atmosphere. And if we look at the longer time range, actually we also have the land impact and ocean impact. These are the important predictability, sources of predictability for some seasonal and seasonal prediction. And this slide just shows the time scale of land impacts. So this figure from the paper of Paul Meyer a long time ago, showing the maximum periods of increased predictability scale by land initial conditions. Of course, these maximum periods are different for various regions or seasons, and it's also different for variables like 2-meter temperature versus humidity. But basically, this figure shows in some areas we have a longer time scale, the influence of land in a longer time scale. I would like to show that how the snow conditions actually has an impact in seasonal and regions in this topic. And usually, or in previous studies, we often use the model sensitivity experiment to investigate the land impacts for S2S prediction. This is one example from a paper by John et al. Published in Journal of Climate, they show that the change of potential predictability of surface air temperature using the snow depth initialization. So if we compare the initialized or the uninitialized, the two experiments, then we can know that where and when we have the snow impacts. Yeah. So in this experiment, if we have the one experiment using the realistic snow condition, and the other uses the just shuffled snow initial conditions, and we can compare the scale of potential predictability. Right. So, as I said, the previous studies often use the statistical analysis, like the correlation or regression analysis, or model sensitivity experiments. Some drawbacks of the existing method, for example, the statistical method, we often use the lagged correlation analysis or lagged regression analysis, but you may know that the correlation doesn't imply the causality. So even we have the correlation between two variables, it doesn't mean that one variables or the one element has caused the other element, the variability. This is just an example of that kind of situation. Here, from the Macro and Barnes paper, and here on the left, on the top, we see the lag regression analysis. The color shows the significant area, and here they investigated the lag regression between mean 3.4 SST, I guess, the ENSO and surface temperature. And because of the snow variation of the ENSO, even we take the lag correlations, we often get the similar pattern if the ENSO precedes the surface temperature or the surface temperature precedes the ENSO. So we can't use the lag regression to disentangle the causality because of the slow varying ENSO characteristic. So on the bottom, they show the so-called Granger causality analysis. Then we can see for example, ENSO causes the surface temperature. In this case, we don't see the surface temperature cause the ENSO. Of course, we know that the land doesn't cause the ENSO variability. So this makes sense. But if we look at the lag correlation or regression analysis, actually they are not very efficient or useful for analyzing the causality. The other approach is the model experiments. The model experiments also have some shortcomings. So the first one is it's impossible to compare the land influence assessed by model and observations. So we can assess by assuming the perfect model and assess the land influence using sensitivity experiment, but we don't have such a actual condition in observation or real world. So this is one shortcoming, limitation. The second shortcoming may be the estimated coupling strength depends on the model used. So even we use the sensitivity experiment, as I said, we assume the perfect model. The model is perfect, but we know that the land atmosphere coupling process depends on the how we formulate the land atmosphere interaction in the model. So we can't really trust the simulated simulations as a truth. The third one is so if we part out or change the initial conditions, we may have some unbalanced conditions, and that may affect the results of the sensitivity experiment. The last one is a technical one, technical reason, because we have to run the numerous simulations, we need a computational cost. So in this study, we apply the take the different approach for evaluating this knowing fund. I will shortly introduce the new technique, the near-neighbour information flow. And using this technique, actually, we don't need the model simulation, and we can compare the results with the observation and models. So we thought that this technique is has an advantage, so we tested this approach for the land atmosphere interaction. So this is just a reminder. This slide reminds you about the entropy. So in this talk, I will use a kind of information theory, and this slide is a slide I showed last week, and okay, if we have the autonomous system, dynamical system, described as like this, the x is the state vector of variables, and f is a function of the time evolution of x. And after some mathematics, we can get actually the entropy of x is the integral divergence of f. This is a very natural way to describe the uncertainty of the prediction, if you want. Here I'm showing the schematics. So the entropy is how quickly or how large the one solutions diverge in the future. So as we see here, we can derive these equations from the time evolution equation. So information entropy has actually physical meaning, and the entropy time evolution is derived from this equation. So really rigorous description. This is a rigorous expression of the uncertainty in the equation. So the method we use in this study is near-neighbour information flow. Here I just took a picture of two authors discovered this method, and one is the Professor Sang Liang at the Fudan University, and one is the Professor Richard Dean. They proposed this method. So let's think about the autonomous system like this. And then immediately we got the Liouville equations of this equation. So we can describe the time evolution of the probability used like this. We can show this. And as I said, we can get the time evolution of entropy of this based on this equation. And if you look at this equation, it's very natural because we just compute the change of the entropy in time is just diverse, how the variables diverge in the future because of the f. You can just look at this paper. This paper shows how these are derived. And in the real system, this is a deterministic system. We don't have the noise or stochastic forcing. But in reality, we have the stochastic term, and that means we need some stochastic term in the equation. And probably it's difficult to explain in the short seminar, but after some computations, we can derive the time evolution of entropy of a variable xi, x1 as the kind of expression without any assumption or any approximation. And they also consider the entropy time evolutions without the influence of the variable x2. Here we are talking about the equations, two-dimensional equation. So we have x1 and x2. And again, there are some calculations, but we can get the final results like this. And if we look at the difference between the full entropy of x1 and the time change of x1 and the time change of x1 without the influence to, then we can derive these equations. But if you look at these equations, actually we need the actual form of f. So in reality, we don't have the function f. Then they also deduce the rigorous formula to compute the causality without knowing the function f. And if we assume that the time evolution is a linear function, then we have a relatively simple equation like this. And here, C is the covariance of, and the subscripts indicate the variables, x1 and x2. And D1 is a forward differential of, for example, this case, forward differential of x1. So if you look at this equation, it's very simple and easy to apply for real problem. And furthermore, we use the causality normalized by the total chain of entropy. And the exact formula or the equations can be found in the paper. In the first part, we just focus on the snow impact over Eurasia. So this is the first paper we did, try to test this method, and we also did the sensitivity experiment to check the results. So over Eurasia, if we apply the EOF analysis over Eurasian region, by the way, this is for the case of November, we have two dominant modes. Actually, the explosion rate are similar, 11% and 10%. So we have two modes, and one is we have a peak in the western part of Eurasia, and second one is a dipole pattern. So in the previous studies claimed that actually this dipole pattern causes some atmospheric circulations. But we want to test this hypothesis. Right. First, we looked at the correlation. As I shown in the introduction, actually, if we look at the correlations, this is a simultaneous correlation between the 2-meter temperature and snow. We see the all blue. meaning the negative correlations. This means that if we have the cold temperature, we have more snow, or we have more snow, then that may lead to this cold temperature. So actually, the correlation doesn't show some causality or the causal mechanisms in the process. So we applied the normalized information flow analysis, real-time information flow analysis for snow cover and 2-meter temperature, and we got these results. On the middle, I'm showing the causality from snow cover to 2-meter temperature. On the right, I'm showing the causality from 2-meter temperature to snow. We are more interested in the causality from the snow cover to 2-meter temperature, of course, because we want to know that how the snow cover actually changes the 2-meter temperature in the future. Right. Then we can notice that, for example, over a western part, West Eurasia, even we looked at two different analyses, the MENA2 and the ERA5. Both data indicate that the strong causality from 2-meter temperature to snow over western part. See? If we looked at the East Eurasia, actually we found that over East Eurasia, we found a relatively strong causality from snow cover to 2-meter temperature. So these results show that if we are interested in the influence of the snow cover on the 2-meter temperature, here East Eurasia is the region where we have this snow cover impact on the 2-meter temperature. Of course, here I'm showing the results for the November. But if we look at the other seasons, actually the information flow varies largely depend on the season. And because we focus on the November, because we know that the November is some in-between season where we have these snow covers, strong snow cover impact on the 2-meter temperature. Right. Then, of course, this is the results of the kind of new techniques. So we want to underscore the results using the model sensitivity experiment. So we did the simulations, the two simulations. One is run initially. One experiment, we took the run collisions with 5/5 highest and lowest years of the dipole pattern. So we compute this the index of using the EOF, and we took the fifth highest and lowest years, and we applied this initial conditions for different atmospheric interactions. So we randomize the atmospheric conditions, but we keep the same initial conditions for the land to see extract the land snow influence in the ensemble simulation. And in other experiments, we just we did two experiments using the fifth highest and lowest experiment, and we compared the results. So, here's the results. The top panels show the results for week 1, and the bottom panels show the results for week 4, the anomalies of snow cover, surface temperature, and sea level pressure. And in the first week, we see some anomalies because anomalies. Now I would like to focus on the week 4. So if we look at the week 4, actually we found that the larger anomalies over the western part of the Eurasia. This is consistent with the causal analysis. Again, so we believe that these snow initial conditions actually has some impact on the surface temperature over these regions. So summary so far, so we attempt to apply the causality analysis for the snow and the 2-meter temperature process, and we found that the strong causality in the western part of the Eurasia. And the results of the de-improvement causality is supported by our model-centered experiment. So let me move on to the second topic. So as I said, the snow impacts really depend on season and regions. So we want to look at the overview of the snow impacts for northern hemisphere regions. So first, in this slide, we see the standard deviation of weekly average snow cover. This is just showing the change of snow cover. By the way, the black line shows the snow cover of 50%. So we see the time evolution of the snow cover from summer, northern summer, and winter. We have expansion of snow cover. As time evolves. And we also see the retreat of the snow cover area in May. So even just looking at this figure, we can immediately imagine that the snow impact actually has a strong seasonality. Then we first just check the 2-meter temperature snow cover correlation. Again, we just see the blue curve. That means we see some associations, linear associations between the 2-meter temperature and snow cover. But we see that some different regions seasonality. We also look at the snow water equivalent. The snow water equivalent, for example, we see some different features. We see the red color here. Red color means we have the positive correlation between 2-meter temperature and snow water equivalent. We didn't explain very details, but we're guessing that probably the lower temperature could provide more snow or something like that because of the air can hold more moistures. Now I'm showing the 2-meter temperature and snow cover, de-improvement information flow results. Right. On the by the way, this figure shows the results for autumn, September, October, November. And on the left, we see the causality from snow cover to 2-meter temperature. On the right, we see the causality from 2-meter temperature to snow cover. And at first look, we can see that the regions are similar. So that means that we have the two-way interactions. I mean, sometimes the snow cover create the 2-meter temperature variability, or so there are two-way interaction. But we are more interested in the influence of the snow cover to meter temperature. And we found some hot spots or cold spots, whatever, the sensitive regions of 2 meter temperature on snow cover. For example, in September, we see the hot spot here, the cold spot here. And in winter or in the late autumn, we see the large area of the cold spot. Now I'm showing on the left the left figures are same, and the right figures shows the results for the spring. And if we look at the spring, we found some sensitive regions here, here, here. And yes, but this is not the figures in autumn is not mirror image of the spring. So there are some interesting seasonality over Western, over US or others. Probably we also interested in the US or North America. We found that some areas here. And okay, over these regions, these results of course were consistent with our previous study. We also checked the results using the snow water equivalent. Again, we got very similar results as to the snow cover. But sometimes we see the slight difference. I don't know the reason. We didn't discuss in detail, but in general, we see the similar. We found a similar sensitive region. So these results actually indicate that where we can benefit again the subseasonal prediction skill because of the snow conditions in the initial function. Right? So if we have more realistic or analysis of initial conditions, we could gain some skills over this issue. By the way, this is a result from ERA 5 again. In general, results are consistent. Now, I would like to focus on the seasonality from particular cold spot regions. I selected the regions as cold spots. The boxes show the several cold spots, and this is a time series of time evolution, seasonal evolution of causality. And blue indicate the causality, normalized causality from snow cover to 2 meter temperature. And red is causality from 2 meter temperature to snow cover. Again, we see the two-way interaction over most regions. But probably we are more interested in the blue bars that indicate the snow influence on 2 meter temperature. And for example, in northern area, we see that just one peak in the seasonality. In exotropics, sometimes we see the 2 peaks of the season in the causal influence because the snow areas migrate, and over the exotropics we have 2 transition seasons in one. And we also looked at the results of the S2S model. These results are from the WWRP, WCRP S2S projects, and we compared. Now, here I'm showing the results for JMA and disentangling model, but we also analyzed the CMA model as well. And we immediately noticed that the JMA model really underestimates the snow cover influence on the 2-meter temperature. On the other hand, the ECMWF model somehow showed the reasonable snow impact on the 2-meter temperature. So that means that there is a deficiency in the JMA model. And this is the results for the spring. Again, yes, we see a very big snow cover influence in JMA model. Actually, my colleague working on the snow scheme to improve this characteristic reasonably, we got reasonable results with the device scheme. So hopefully we can fix this problem. Anyway, so yeah, this is just the same figure for 3 models. Now we have the CMA model. CMA model is another model reasonably captured, slightly underestimate the snow cover influence compared to the analysis, but these two represent reasonable snow impact. And the other question is how actually the snow impacts on the potential predictability of 2-meter temperature. So because we know that the 2 models, the one ECMWF and the JMA model, they are quite different in terms of the snow influence. So we are interested in the impact of the snow on the potential predictability of surface temperature. So here I'm showing the potential predictability of 2-meter temperature for week 2 and 3, 2-week average, right? And these are ECMWF, these are JMA. Here I'm showing the difference between ECMWF and JMA. And we found that, for example, okay, here we see a red color. By the way, I evaluate the potential predictability using the correlation. So we can assess using the ensemble prediction, we can get one ensemble member as a surrogate observation, and we can compute the correlations between the one surrogate observation and the rest of the ensembles. And we can repeat this exercise to assess the potential predictability. Okay, now, so for example, here we see the red color. Actually, this region is consistent with coincide with the hotspot region. If you remember, for example, here we see the hotspot region, and exactly same regions show that the potential predictability in ECMWF model is much larger than the JMA model. This also supports that in JMA model, actually, JMA model can give some potential predictability over small sensitive regions, and ECMWF model does. So that's why we see the difference over these regions. And also, we found that other regions also, there are some regions where we have more potential predictability of surface air temperature. in ECMWF model than JMA model. So again, these results also support that the snow provides some subseasonal predictability in surface area temperature. So we need to really, the model should represent this process as observed or likely reality. So to summarize, this study investigates this sub-monthly causal relationship between snow cover and surface temperature. And we can also apply this technique for the models, and we can compare or validate the representation of the models with the observations. So this is kind of useful diagnostics for models as well. So let me just quickly go through our recent topics. Actually, these results from a paper currently under review in Journal of Climatology. My postdoc is working here, working on this topic. We focus on the snow hydrological effect in this study. So I show the results for the spring and autumn because we are mostly focused on the snow albedo effect. But here we focus on the snow hydrological effect. That is, so when snow melts, actually the snow provides soil moisture. And the snow moisture also has some influence on the atmosphere. So we call this process as snow hydrology, snow hydrological effect, and it occurs in summer, basically the melting season of snow. So here I'm showing the standard deviation of snow water equivalent soil moisture, 2-meter temperature for May and June. So in May and June, I forgot to put the satellite map, but if you look at the MODIS image, we can know that actually we have this snow area just only in the northern part of the US in summer. So we expect that we could have some snow hydrological effect over this region, West Siberia. And this region also shows the large variability in subseasonal time scale. By the way, yeah, this is the standard deviation weekly average of these variables. Then we computed the composite mass of 2-meter temperature with respect to the soil moisture conditions over this region. And basically, these figures indicate that if we have less soil moisture, we could have a warmer surface air temperature, or if we have the more soil moisture, we could have a lower temperature, or vice versa. So we see some association again between the soil moisture and surface air temperature. And also, we can do the same exercise using the normalized real climate information flow. Here, I'm showing the information flow from snow water equivalent to 2-meter temperature in June. Of course, we found that the other regions also had some large values, but over West Siberia actually stands out as the large information flow. So that means now we are looking at the connection or the causality from snow water equivalent to 2-meter temperature. And he also looked at the atmospheric flow. We looked at the atmospheric flow we did the same composite analysis for 250 hectopascal geopotential height, and we found some anomalies. We found some anomalies associated with the soil moisture conditions of these regions. So our question is really the land could contribute to the atmospheric flow. In first approximations, we expect that the atmospheric flow can melt or delay the melt of the snow, and that causes some variability in the snow water equivalent and soil moisture. But we could have some impacts from land to the atmospheric flow. By the way, this pattern actually resembles to the so-called British Bical corridor technology pattern, which is a direction pattern over the polar frontal jet. Yeah. On the bottom, I'm showing the typical pattern of the British Bical corridor pattern over areas. We see some slight shift of the phase, but basically this is the EOF, the analysis of EOF, so we can explain why we have some slight shift of the phase. Anyway. Then we also looked at the vertical latitude cross section of geopotential height anomaly, and together with Takaya Nakamura wave active facts. By the way, the Professor Takaya is a different person. Anyway, yes. So if we look at the West Siberia regions, we could see slight slanted vertical structure. So that indicates the land influence could propagate to the atmosphere. And actually, if we look at the wave activity flux, we see vertical propagations. So that indicates that we could have some forcing from the land to the atmosphere in a particular phase. And this anomalies also could explain using the heat flux. So the soil moisture conditions actually change the partitioning of the energy of the surface, and that can change the sensitive heat flux or latent heat flux, and so depending on the soil moisture conditions, we could have some impact on the surface flux, and that could also impact on the atmospheric flow. This is what these results imply. So in the last part, I just highlighted the snow hydrological effect. Hopefully this paper will be accepted soon. Okay, in the very last part, I just introduced our ongoing work. So we could discuss technique for example, soil moisture. So here I'm showing the causality, again the same property, the Young-Kleeman information flow for soil moisture, from soil moisture to meter temperature. I'm showing the information flow for Asian monsoon region, summer monsoon season, May, June, July, August, September, October. And I'm surprised to see that really we see seasonality, strong seasonality in the monsoon regions. For example, if we think about the monsoon onset, the timing of the monsoon onset, we know that the Asian monsoon starts from the in the very southern part of the India, around Kerala, and we could have the monsoon onset. We have the monsoon onset in June over this region, and that also extends to the northern part in July. We clearly, if we compare the monsoon onset season, by the way, this video, I forgot to put the side difference, but yes, this is some paper in previous paper shows that yes, as I said, we have the monsoon onset in June over central part of India. Actually, we see strong soil moisture, strong influence from soil moisture to meet the temperature over these regions. So monsoon regions actually are affected by the land conditions. So over the monsoon region, I think that the land atmosphere interaction is important to give better succinct application. And we also found a very interesting results. So if we look at the literary season, the midst of the monsoon, actually we have a monsoon literary in September over the Indian regions. Again, we see relatively large causality over here. So in the monsoon onset season or literary season, month, we could have some have strong landing influence on surface temperature. I have more detailed analysis, but because of time, I can't introduce. Actually, I'm still working on this. Lastly, I would like to just give us some conceptual framework on the land surface. So, more than 10 years ago, the famous paper, Selim Latin et al. Showed that this kind of figure. This figure shows the x-axis is soil moisture content, and y-axis is the ratio of evaporation and radiation. So this is the exchange. So in very wet, dry conditions, of course, there's no evaporation. So we don't have the evaporation here. That's why we have the air itself in very dry region. And if in the very wet regime, again, we thought that this value is actually saturated, and land soil moisture can change the ratio of the energy partition. But based on our results, it seems to be a bit different. So here I'm showing the normalized information flow over 40 degree tropical regions or subtropical regions. And x-axis is Bowen ratio. Basically, the Bowen ratio represents the wetness of the soil. And y-axis is the net shortwave radiations. And this figure shows very interesting feature. First, if we look at the dry regime, we see the gray or yellow color. That means soil moisture, snow water volume, information from flow from soil water volume to meter temperature. We influence of the soil moisture and temperature, right? And if we looked at this part, so from top to bottom, we see the gradient of the value. So in this region, actually we have less shockwave radiations, and in that region we have again a weaker influence of the soil moisture on surface temperature. And if we look at these regions, we see the blue colors in this side and green color this side. So we define the transition region here. So if we have more wet conditions, then we could have a larger soil moisture influence. And this region, the soil moisture sensitive, we call the soil moisture sensitive regions where we could have the soil moisture impact on the 2 meter temperature. So with this diagram, I would like to propose renew the diagram as shown in the previous studies. And interestingly, in the very wet region, we still have some soil moisture 2 meter temperature. So I think it's better to revisit this problem using the new knowledge. So yeah, this is ongoing work. I don't have summary, but I would like to write a paper soon if I have time. So thank you for your kind attention. Oh, shit.
Yeah, I think we have time for some questions.
Yeah.
If you have questions, also, I don't know if there's someone listening to us from remote.
I can't see the audience. Please speak up if you have questions, if you are online.
Okay, maybe we'll start with Franco.
Forget about the mathematics.
I was intrigued by this last part of the impact of to the soil moisture. So I remember many years ago with our friend looked at something similar, so impact of snow directly on the monsoon, maybe it was much more jump. We found some result at the time the ensembles were very small and the models were maybe not as good as now. So the impact you see is to the temperature. So if you usually in summer, for example, or in India, when you have a strong monsoon, the 2 meter temperature goes down because it rains. So how would you interpret these results in terms of the strength of the Asian monsoon?
First, yes. In previous studies, this is an old index. There are other index, but in all studies, for example, these studies propose the index using correlation between evaporation, latent heat flux, and temperature. Yes. If we look at this figure, this equation, actually there is no soil moisture variables. So this is a kind of approximation, assuming the the soil moisture change the latent heat flux, and that could change the temperature. But there's no guarantee in this chain process. So in our analysis, we directly assess the causality from soil moisture to the temperature. So I think this is a more direct way to assess the soil moisture impact on to meet the temperature. And yeah, as I said, this is a very natural way to assess the impact in terms of the entropy. So yes. Then what is it? Yes.
Yeah. So this is an analysis, a local analysis. So,
yes.
so the points you're showing are different regions where you have different conditions.
Yes.
Yeah, so I was trying to, my question whether you could also see some remote effects. So for example, what we saw was that when the conditions over Siberia changed, for example, in this area in spring, that is one of the hotspots that you have shown, that seemed to have a delayed effect on the monsoon. So I'm wondering whether you are also looking at the delayed effect of.
We haven't looked at. It's a very interesting point. Because of this simple analysis, we just evaluate the causality between two variables, but we could apply the variables between the remote variables, like if we take the soil moisture here and we can compute the surrounding region, then could apply, but I haven't yet studied such impact. And yes, as you said, after the monsoon onset, we have more tropical convections, and actually we have less insolation, this solar radiation. That explains why we have in the monsoon peak season, we don't see the large causality, because as I have shown in the diagrams, if we have the less solar radiation, we have less influence of the soil moisture. That explains, also the seasonality of the soil moisture impact in the monsoon season. This is a really interesting point. I think I'm investigating this point now. Thanks.
Maybe I can. Okay. Just one more question on the possibility to investigate on the remote connections. So, do you think this technique can be used to see if the snow cover over the Siberian area has some effect on the evolution of the stratospheric polar vortex? Because we know there's a part of the recent scientific literature that is trying to highlight possible connections during autumn, maybe.
Yes, I think it's possible. If I remember correctly, we also computed the causality between the average snow cover over this region and sea level pressure, and we got a slight remote influence in the sea level pressure in the causality analysis. So also that result was consistent with the model sensitivity experiment. So we can use the causality analysis to investigate the remote influence. For stratosphere, we haven't looked at, and sometimes it's difficult to separate the mechanisms. Of course, the large-scale atmospheric flow can also have a very large impact on this snow cover. So even using the model experiment, it's very difficult because if we look at the week 2 or week 3, we already have the impact of the atmosphere on the snow. So probably if you nudge the snow condition, we could do it. But sometimes it's very sensitive to the model and we have different results. And still, it's challenging, I think.
Yeah, probably the issues you highlighted in one of the first slides about modeling soil processes anyway also says to us that there's quite a lot of room to improve model prediction by improving the soil processes and surface processes.
So these studies just focus on the surface temperature and the snow soil moisture because we think that it's probably low-hanging fruit than the limiting effects. Okay. So that's why we started on this topic. But we want to explore more. Yeah. Since Andre is here, I just add something related to vegetation. If we looked at the causality, of course, we see the migration of the snow cover. But for example, over this region, we don't really, this region, we don't see a very large causality, even with that. It seems that there is some brown region of the causality of the snow. Actually, this region is, if we look at the vegetation, there are many trees. More trees means less albedo. So the snow albedo effect may be less effective over this region. That's why we could have less snow impacts on the surface temperature. We need to check with the data, but based on the analysis of the models experiment, we found that we didn't discuss in detail in our paper, but this is also an interesting point.
Yuhei, I have a question. You showed that ECN model was better than JMA in capturing the snow cover effects on temperature. And you also mentioned that you are working and you are fixing. Yes. So, which were the reasons?
Oh, my colleague changed
related to initialization or
model. Yes. Okay. So we know that, for example, in the model, we calculate the snow cover using the snow water equivalent. In the model, the snow cover is a diagnostic variable to compute the albedo or other properties. But in JMA model, it doesn't very good. Doesn't work very good for snow cover. So my colleague changed, and he also changed many detailed snow processes to tune the melting timing, and he did many things. And it seems that I just looked at the impact on this scale, and I suddenly I found that the influence of the region where we have the scale improvement actually coincide with these regions. So I believe that what he did is really fix this problem.
is the model.
We haven't really diagnosed the model yet, but I guess he improved the snow cover impact in the model, I guess. Yes.
Another question. Since you use MERA as the analysis to verify, which I think is more fair than using ERA5, because I would guess that would favor this CNR model since it is not. But just in general, I wonder, is there any difference? These ideological variables, they are model dependent. They are generated by the model physics. So I'm always wondering when people trust too much what comes out from the reanalysis. So if you compare MERA with ERA5, are there substantial differences?
Yes. Oh, in general, we see a similar. By the way, this figure. Oh, this one is more. Sorry. Okay. Let me see. I have the figure. Okay, this. Oh. For example, okay, this is the results using the ERA5, not MERA, and the green circles are the hotspot regions where we found the strong influence in MERA analysis, and we also see the same figure. But other regions, like for example, over Tibetan Plateau, in ERA analysis, we found that ERA has excessive snow because of the model parameterizations, and we exactly found the strong causality from snow cover to the temperature. But I think that this is not the correct feature. So yeah, there are uncertainty. It's fair to say, okay, if we look at the different reanalysis, we see some difference. But that means there is uncertainty. So even using the new technique, it depends on the quality of the reanalysis. We always need to check the multiple analysis to get the robust conclusions. Yes, thank you for your question. But if we look at the modest image in summer, we have less snow in observation. We have less snow, so I don't expect that kind of very strong snow impacts. But if we look at the ERA5, because of the bias in the analysis, yes, this will not come.
Okay. If you have any more questions, comment? No? Okay. Yuhei, thanks again for your very interesting seminars, both. Yeah, so thank you. It was great.